as you could see in the previous segmentations, there can be a lot of misclassified pixels. And one way is to improve procedure, everything coming before it. But sometimes it's actually easier to handle that afterwards. And that is where we come to morphological image processing. And when you do that, it's a kind of filter that we are talking about that looks at the neighborhood constellation of black and white pixels. And it looks at the concept that things that belong, pixels that belong to an object, they are mostly connected to it somehow, and its neighborhood, from its neighborhood, we can tell this pixel belongs actually to the object or it doesn't belong to the object. And if it's noise, it's just isolated pixels spread out all over the image, and those can easily be rejected. And that can be adjusted. Oops, let's see, I need to go on that one and that one. So let's look at this simulated example. It should be just a cross, which is very noisy. And you can see that the thresholding didn't do very well. We have very many false positives. We have many false negatives. And now we want to clean up this, saying that we couldn't fix it much better with the filtering before. And let's look at what we can do. First of all, we want to look at a little bit about what is a neighborhood. There are different shapes of neighborhoods that we are talking about in morphology. The closest neighborhood is just the pixels surrounding the pixel itself. That's the very simple one. It could be just up, down, and left, right, or it could be all pixels around it. And the larger neighborhood you select, the more time, of course, it takes to compute. And one effect is if you work with the large neighborhoods with gray levels, then you can get also a smoothing effect. So then we are back into the convolution case. And if you have too small items, too small neighborhood, then you can't cover large mistakes or filling large holes. But that's a balance that you have to select. There is always, when you do this kind of modification, there is always some give and take. So what we have done until now, we have done the filtering with different kernel sizes. Morphological operations are coming. Different things that will come in the next lectures, the coming weeks, are component labeling, distance maps, and also tracking of displacement in images. Then you can also look for different neighborhoods. And the neighborhood in many work package, in many toolboxes is called structuring element, or in Python, in the scikit image, it's often called SLM, so for structuring an element. But that's the same as the neighborhood. And typically in 2D, we are talking about these two neighborhoods. Turn out quite small, unfortunately, here on the screen, but you have two classic ones. If you have just the direct neighbors to the central pixel, we are talking about 4 connected neighborhood and 8 connected neighborhood. And they, of course, also, if you run them over the image, they give also different appearance and in the result, in particular if you use them in different advanced algorithms afterwards. Some other types of neighborhood shapes we have. These are neighborhoods provided by scikit image using the different names here. So we have disk, cross, oops, no, there it is. So disk, cross, horizontal line, vertical line, star, octagon, and then using different sizes. And you can see in the beginning a disk 5.5 doesn't really look like a disk. When you get up to 11, then yeah, it starts getting something that looks like a circle, but that's the limitation of writing these neighborhoods on few pixels. The octagon comes out pretty good, almost looks more than like a circle than the disk itself. So that is the question, how it's implemented. You can also have neighborhoods in 3D, and the two more simple ones are called 6 connected. So that's up and above and below, and then left, right, or the direction north, east, west, south. And the 26 connected is the whole cube around the pixel. It's also quite common to use 18 connected, and when you do 18, then you remove the corner voxels from the neighborhood, and then you get 18 voxels in the neighborhood. And when you work with this neighborhood, there are two basic operations that we talk about, and they are erosion and dilation. And erosion is like you have in nature. It takes something off the structures. So you peel off some kind of skin from the image. Dilation, that's the opposite, and that's growing. So it's adding a layer to the objects. And combinations of these you can is what you use in order to remove misclassified pixels. Looking first at erosion and dilation in action. And here I'm using the scikit image versions. So we have in scikit image, there is a morphology subsection, and there is dilation and erosion. And in this case, I'm using a structuring element, which is just a 4 connected neighborhood. And I have this original image, and if I apply the erosion, I only get these pieces left. If I apply the dilation, then you can see it grows up pretty much. And if I now would play with the size of the structuring element using different shapes, so for example, having a line like this, a vertical line. Oh, I didn't execute the first. Sorry about that. I forgot to execute that one. Where is it? Here it is. Good. Must have missed. No, that's right. That's right. So there is the right slide. So now it should work. Again, not. Okay. So in that case, I'm import scikit image dot morphology as morph. So now it works. But here I'm a bit confused that it takes it like that. Okay. So let's go for that one. That was the original one. If we do the full box like this, that's why there is a hidden line that does the plotting. So here you can see there is, if I have the full neighborhood, there is only one place here that actually takes is covered. Otherwise, it will erode. So the erosion requires that all pixels are 1 in order to give a 1 in the center. The dilation, on the other hand, only requires that there's 1 pixel that is 1, and then it plots in the whole object. of the structuring element. And that's why you get a pretty blobby thing here. So now we can play with different shapes, like the line I tried before. So, and then we can see here that you can have a full line all the way till here, and then it's fine. And then this one is not a line. This is too small, and there is a line of 3 pixels here, and you can get 1 here, and that is also why you get 2 pixels around here. So these are the different cases of erosion. You can test it out yourself afterwards and see how it behaves. And I continue. Let's just look at what's happening here. If we look at the dilation itself, you can see here that if I have the central pixel is a 1, then it will plot in this structuring element. And in this case, it was a cross, so these 2 pixels will be added. If I take this pixel instead, then we draw in a cross, and then we get those pixels added. And that is how we get this final result. And looking at the erosion instead, then you can see that if the cross is completely full supported, then I get a pixel, otherwise not. So here is also a nice place where you can see that the cross is actually there, and you get a single pixel, and then the result of the dilation, erosion comes here. And I see that I have a typo. It shouldn't be dilated here. Then there are 2 other operations which are combinations of erosion and dilation, and that's opening and closing. And these operations are very useful, in particular to get rid of the misclassified pixels. So you have, for example, the original image, and we apply again the cross structuring element, and in the image, so this hole will be filled and this hole will be filled, and then you have closed it. And the operation of closing is that first you dilate by a structuring element, and that's actually the dilation, as you remember, actually filled out this central part. And then afterwards, you apply an erosion, and then you go back again and come almost back to the same structure. What is happening, for one thing, is that this gap is filled and this hole is also filled. Other cases, you don't see a difference, like here. Here it's filled up a little bit. And if you do opening, that's the opposite operation. Then you first erode to take off a lot of structures, and then you let it grow up again a little bit. And then you get this space invader shape from this structure. And looking at the details again, so we have the morphological closing. Then here you can see in the blue, here you can see what the operation of the dilation, and the green is what is remaining after we have applied the erosion. And then you get the closed results as this. Which operation you use between opening and closing depends a little bit of what you want to achieve. Sometimes you even have to apply a sequence of them, because you have some misclassified pixels in the void, and you have some misclassified pixels within the sample. And then you have to decide how to remove them best. And that's also the order in which you do it can also play a role. So that is a little bit experimenting in the beginning to see how your images behave best with these operations. Also, which size you need. Maybe you need a smaller size to do the closing than you need to do the opening. Who knows? It depends on how you set the thresholds. And in the end, you want to have a structure that best match your ground truth. So you have to, that's a bit of experimenting to get that right. Then there are some problems when you do the segmentation, and one is the partial volume effect. That is thanks to smoothing from the from filtering, from also from transfer functions of your imaging system, you have smooth edges. And sometimes it's also that, so that gives you one uncertainty. The other thing is if you have a continuous object and try to discretize the image, depending on how small your pixels are, you cannot really find the perfect transition point in between black and white. So there is some uncertainty if the pixels along the border is classified as object or not object. And that is what you can see here. For example, if you have this, this should be a ball or a disk in each case, but depending on which resolution you have different volume fractions. You can see here that if you try to represent the same thing with 10 pixels and you represent it with 500 pixels, you can see that the volume fraction is actually increasing the more detailed your work, the more detail you can measure. Sometimes this is the only you can get, and then you have to be aware that you have an error in your segmentation purely because you can't resolve the objects. And the other thing is when you go into 3D, then it's also a question, when is a sphere really a sphere? And which radius do you need in order to get something that looks like a sphere? The first one is just a three-dimensional cross. And then you get some kind of boxy thing. And I think this is radius 5 or something, 4 or 5. Then it starts actually looking like a sphere. And I did a calculation where I looked at the volume error if you do the discrete volume over the analytical volume of the same radius. And then you can see that around 10 pixels radius of the sphere, then you have still around 1% error in volume measurement. And if you go down to very small radius, then you have really many percent error in, so between 20 and 50% error in how you quantify the volume. So this is important to be aware of when you work with images and want to look at small items. You have really, so the sampling frequency tells you how much, how small objects you can detect, but you have to be aware that you have to oversample a lot to be able to represent objects in the way they are supposed to look. Another thing is about scaling. If you start scaling an image, going from 500 pixels down to 10 pixels again, you can see that first, if you do a downscaling, and this is the original, then you have just a straight line. And if you downscale, sometimes you have intermediate gray levels along the edges. Like these two here. And so you can see here are some gray points. And here's another case where you also can see the gray pixels. And this is something you also have to be aware of. When you do downscaling of the data, you may get also these partial volume effects because you can't resolve the shapes that you want to. So this was also a short one. I need to add a little bit more. One thing I can add afterwards, but now first look at what we did today already is we looked at the image formation process on how images are made. We looked at how the histogram can be used to find where we want to set the thresholds. and also how we can evaluate the performance of these segmentation methods. Basic operations for morphological image processing, they are used in order to remove misclassified pixels, which we may have many of. And actually, that's a point that if you run these ROC curves, receiver operating characteristics, you can actually do that after you have applied the morphological operations and see what happens around the images with those. And finally, we looked also a little bit at how well you can represent structures with discrete images. So if you try to segment small objects, you can't expect to get a good shape out of it. Now, I would like to actually touch back on a question I got after the lecture last week. So this is something coming from the filtering theory, and it was a question about VINO filters that you asked. And I don't know if you saw it already, but I did an attempt of using the Fourier transform to do a signal model matched filter. And that I need to look up. I think it was here. Now, first I need to run that one. No, where is it now? Yeah, there it is. So I need to load those images. So in this example, I'm using this scene with the balls, and I have some noise in here, and I want to filter it in the Fourier space. And what I played with in the beginning was first looking at the Fourier spectrum of the image. I looked at the spectrum of the noise and looked at what it looks like together when it's a sum. Now, during the lecture last week, I tried different shapes of filters. And one that was quite interesting was to look at this one, where you have a cross that more or less just focus on the middle of the spectrum. But another way that you can work with is the so-called VINO filter, which is a filter that takes into account one thing is the point spread function of the system, and on the other side takes into account the noise power spectrum, and then of course also the signal itself, the power spectrum of the signal itself. This looks pretty messy, and you have to know a lot in order to use it. So one thing is you need to know the point spread function of your imaging system. The other one is you need to know the power spectrum of the signal, so that it's a noise-free signal, and you need to know the power spectrum of the noise itself. If you have the special case that you know that you have additive white noise and the transfer function is equal to 1, then you can reduce that equation into this equation, which is much simpler. So it's a power spectrum of the image, and you have only a constant level of corresponding to the variance of the noise. So in cases we have the power spectrum of the signal much greater than the variance, then the filter function is equal to 1. If we have a power spectrum much less than the variance, then the filter function goes to 0. And one thing is we need to know how to all measure the point spread function, no, the power spectrum of the signal. And that is a little bit chicken and egg problem, because if you want to filter something, you don't know what you have. But in this case, in this example that I'm going to show you, I can take the clean image, this one, and compute this power spectrum from that. And now I do some filtering magic. So the first thing is I compute the Fourier transform of the image. And to compute the power spectrum of the image, you compute the Fourier transform of the image times the complex conjugate of the same signal. Multiply them, and then you get the power spectrum. The variance I just compute as noise.var, so it gives you a scalar. And then I need actually to scale it by by a factor, because the Fourier transform, the numerical version, actually has a multiplication, a factor of the image size. So the spectrum has the factor of the image size as additional to what you would expect. So that's why I need to scale up this. Then I compute my filter function, and let's see, yep. And I compute the Fourier transform of the noisy image. And finally, I apply the filtering, which is this filter function times the Fourier transform of the noisy image. And then I do everything, inverse transform again. And what you see now is here is the power spectrum of the, I think that one was the clean image. And this is the filter function, which looks pretty ugly actually. But the important thing is that you have here in the central regions, you have essentially one that lets all the signal through. And if you look in the true signal, you can see that you have some stripy stuff. And that stripy stuff is actually the image structures. So that is also maintained within the filter function. And then we go further away from the centrum, then you go more towards 0 in the filter. And then afterwards, the filter result looks like this. So that was the simple version. So if you want to make it more complicated, then you have to go and measure, actually, you have to know the response functions of your imaging system. Then you can do some, essentially do some deconvolution and sharpen up the images in the same process as the filtering is doing. I don't know about the SciPy VINO filter. This is implemented, essentially implemented using NumPy only. I haven't actually tried the VINO filter. I wanted to look at it from scratch. But yes, you need that too. You need that too. What? That's true. That's true. That's a problem. So that's the chicken and egg problem, that you need to know actually beforehand what you're working with. You can probably, so you can get it in different ways. One is, for example, that you use the power spectrum of the noisy signal. It's kind of not completely correct, but then you measure, for example, out here in a corner, you measure the noise variance. And in principle, what you want, if you would plot it in 3D, you would see that you have a very high peak in the middle, and then out on the corners, you have essentially only noise. So that would be the place to measure the noise strength. You can do it like that, and you get somewhat decent result already. No, you would do it in the spectrum, actually. Yeah. So you would measure in the spectrum up in this region here. That would be a way to get around the chicken and egg problem, but at the cost of not so precise filter. I couldn't let it be when you asked me. So this is also in the lecture slides from last week now.